There are three categories of control charts: variable control charts, attribute control charts, and process-focused charts. A variable control chart tracks continuous data such as cycle time, length, or diameter, so it provides the most thorough information of all the charting options. And while collecting one piece of continuous data is more costly, fewer pieces are required to get sufficient information on a process. An attribute chart tracks discrete data such as pass, fail, good, bad, or yes, no. There can be many characteristics tracked in one chart, and it is less expensive to maintain, but provides far less information about the process than variable control charts. A process-focused chart monitors several characteristics of the same process. It measures only deviation from an established target. Click Tell Me More to read more about control charts. Click Next to continue. When selecting a control chart, you choose between an attribute or variable chart based on the data you have. I'll give you a brief overview of the selection process. Let's start with variable control charts, which are used for continuous data. You must first determine the volume of the data. Low volume, typically one reading at a time, occurs because of expensive data collection or when you have a fairly homogeneous process output, such as a single loan or lease application, or batch of chemicals. In this case, you use individuals and moving range charts. High volume refers to data that is conducive to subgroup sampling. This is the data type we have been primarily focusing on in this training. The X-bar and range charts are the most common option for this data type. Attribute charts are used for discrete data such as yes or no. The first question to ask is if your lot or sample size is constant. If the answer is no, you can monitor for the number of defects per lot with the U chart or the percentage of non-conforming units with the P chart. If the answer is yes, you can monitor the number of defects per inspection lot with the C chart or the number of non-conforming units with the NP chart. Click Next for more discussion of variable control charts. In this training, we will focus on variable control charts because they provide the most valuable information for control, and specifically on a very commonly used chart set, the X-bar and R charts. Some common types of variable control charts are the X-bar chart, which is a plot of sample means collected over time, the R chart, which is a plot of sample range over time, the S chart, which is a plot of sample standard deviation over time, and the individuals chart, which is a plot of the individual measurements over time. Click Next to learn how to generate and evaluate the SPC chart's usefulness begins with deciding on rational data subgroups that will provide the most information about the process. An invoice payment example will help to illustrate proper use of the X-bar and R charts. The processing of an invoice begins when it is received by accounts payable. The administrator must then verify the satisfactory receipt of the goods or services by gaining the appropriate manager's signature. Once approved, they process the invoice and send the payment. To avoid late fees, this overall process must take place within the 30-day time period allotted by the provider. Data subgroups for your control process should consider size, frequency, and number of samples. The sample size for each subgroup should be anywhere from 3 to 5 data points collected in quick succession. That number will represent normal piece-to-piece variability in a short time period, so that unusual variation between subgroups would signal a process shift that should be investigated. In terms of frequency, subgroups should be collected often enough to reflect potential opportunities for change. That might be hourly, daily, monthly, at every shift change, etc. And the number of subgroups should be enough to assure that sources of variation have had time to appear. For the invoice case, each subgroup includes 5 processing times taken from invoices received in the same day. The time is measured in hours. The samples are collected every day for 45 business days. What you should end up with is a data set like this. Click Next to generate an SPC chart from this data. In Minitab, the control charts are generated by choosing control charts from the Stat menu. As I mentioned before, we'll look at the X-bar R charts. But Minitab will also create several others. The resulting charts look something like this. Before talking about the results on this X-bar R chart, I want to discuss the basic components of the chart. The green line down the center represents the process average for the data collected. The red lines above and below that are control limits, meaning that if the data is inside these limits, the process is in control, with certain exceptions that I'll talk about in a minute. Control limits can be calculated based upon a formula that uses the process average and sample size. However, in Minitab, the lines appear by default at plus and minus 3 sigma around the center line. The plus and minus 3 sigma has become accepted practice. Be careful not to confuse control limits with specification limits. These lines do not have any association with what the customer wants. They are based purely on the data that has been collected. So keep in mind that a process could be in control and still not be meeting the customer's expectations. And each data point on the chart represents the average or range, as the case may be, of one data sample. Knowing that, what can we tell about the invoice processing times? Do you think that they are staying in control? Click in other words for some more info on control limits, or click Next to learn how to evaluate the results. This is what a process in control would look like. It shows only random variation around the center line. On the other hand, there are several significant patterns that can appear in the data to indicate an out-of-control state. These patterns fall into the 3 basic categories shown on screen. In the first examples, you see data points that have gone above or below the control limits. Those extreme values indicate a special cause is affecting the process and should be investigated. The second set of examples shows several data points in a row on one side of the center line. This indicates a potential process shift. Analysis should be performed to confirm this possibility and to identify when the trend began. The third set indicates another type of trend, which is 6 or more points in a row that show a steady downward or upward progression. Like the second example, knowing the time trend began can be useful in analysis of the problem. Returning to the charts on invoice processing times, what, if any, problems do you see in the data based on the Minitab rules? Select all problem areas, then click Done. That's right. Between the X-bar and R charts, there are 3 clear problems in the data. 1, there is a point outside the control limits. 2, there is a clear upward trend of 6 data points, indicating some process shift. And 3, there are 9 data points on one side of the center line. Looks like you've got the idea of control charts that will help us decide the control strategy for this improvement. An electronic form can be programmed to require certain fields to be completed before you are allowed to submit it. Based on that information, what is the best strategy to use? Right. In this case, a technique of control called mistake proofing can be employed, which essentially means that a mistake can never happen because the form will never reach the data entry associate unless it is completed fully. Click Next to continue. Now let's review what you've learned in this step. You can now describe the risk management role and function in the control phase, the concept of mistake proofing, and finally the use of statistical process control charts, particularly the X-bar and R charts. Click Next to summarize the outcomes of Step 12 for the GE commercial loan sales case. Reviewing the key parts of a process control system, you'll see that having completed Step 12, we can now finalize it for the loan sales case. We now know our process controls. We are able to mistake-proof both of the X's. That new process must be documented, and the staff involved, such as the data entry associates, should be trained. Finally, we have already modeled the data collection in the pilot environment, so data on the fully implemented process can be collected in the same fashion. That plan should also be documented at this stage. Click Next to celebrate. Congratulations! You've accomplished your learning goals for Step 12 and have concluded the final step in the GE commercial loan sales case. Click Next to return to SIGI for a review of the control phase and a summary of the overall Six Sigma process.